Hi everyone. Suppose you wanted to buy a baby food product for your kid at home. Now, what will you do typically is you open an e-commerce website, go to the search box and input the search keywords for that particular baby food product. Now, you are expecting to find the relevant baby food product options, but let's suppose you start seeing animal food options instead of baby food options. Similarly, you are searching for a table for your work from home setup. Now you wanted to verify the dimension attribute of that table, like what is the height of the table or width and length. But when you open the detail section of that product, instead of finding those dimension attribute, you find wattage or voltage attribute which are relevant for electronics items, as if you are not looking for table but instead looking for a table lamp. Well, you'll be surprised, and I'm sure this will not be a very ideal shopping experience for most of us. Now, you must be wondering why I'm telling you all of this and what does this have to do with our talk today. Well, it's a classic case of item miscategorization, and it's a very important problem to solve in e-commerce domain. And if this problem is not solved correctly, it may lead to a bad consumer experience, as I already highlighted, and may also result in some revenue loss for the organization. My name is Jitesh Mishra, and today me and my colleague Priyodeep will talk about how we are leveraging Graph+ML techniques to solve this problem in Walmart. Now let's get started. So this is our speaker's bio. So as you see, both me and Pradeep have around 10 years of experience working in different industries like retail, e-commerce, securities, and commodities trading. Currently, we are building an enterprise knowledge graph and similarity search platform for Walmart. Now moving on to the agenda. So this slide highlights the key takeaways from this session today. So we'll start our talk by defining what is item category mapping, and then what are the challenges associated with it, and then we'll see the various reasons which motivated us to solve this problem. Now, in the next slide, we'll see what are the current approaches and its limitation, and how we are using the graph-based ML approach to solve this problem. In the subsequent sections, we'll also see the high-level system overview of the graph-based approach and its next steps. At the end, we'll have some time for Q&A. Now, having the agenda set, let's get started with the problem statement. So as some of us might be aware, an item goes through different stages before being listed on the website. Now, item setup process is a genesis of the item's journey on the e-commerce platform. And this item setup process in itself is made up of different minor steps. And one of the important step of item setup process item categorization, which is item to category mapping, wherein we try to map an item to a proper hierarchical category in the Walmart catalog. For example, the baby food product which you are trying to search could be mapped to a hierarchical category called /baby/feeding/baby food/baby food stages. Now, if this item to category mapping is not done properly, it may lead to different problems, and which some of them I already highlighted in our introduction section. Not only that, it takes a lot of post-processing efforts to map them back to our internal taxonomy. Hence, it's very important to have a proper item to category mapping in place. Now, having looked at the problem statement, let's see what all are the reasons which motivated us to solve this problem. So as we see, a proper item categorization results in improved item setup process. So since we have already talked about that there are different steps involved in the item setup, so all the downstream processes of item setup is dependent on a proper category mapping. Like there will be an attribute assignment step wherein an item belonging to a particular category will be assigned certain specific attributes. So if those items are miscategorized, it may lead to incorrect attribute assignment as well. For example, the table which we want to purchase, suppose it's mapped to a electronic appliance category, the system will start expecting a voltage attribute associated with it. Hence, having a proper item to category mapping is very important for improved item setup. Once the item is set up properly, the category mapping also helps us with the effective listing and doing a better assortment planning on the e-commerce platform. Post listing, item discoverability is another important aspect. By item discoverability, mean how easy it is to locate an item on the website. So if there is a proper item category mapping, then in that case, customer will be able to navigate to those hierarchical categories, and even during search, they'll see the relevant search results. As this item is listed, the customers start browsing and shopping those items belonging to different categories. We'll have data around the customer usage pattern and their shopping behavior. Now we can leverage that data to uncover some meaningful insights and provide relevant recommendation accordingly. For example, based on the data, we may derive that some of the items belonging to a particular category are not gaining enough traction. In that case, we can do some course correction and also provide relevant recommendation for that particular category. All of this, along with the relevant recommendation for the better usage of the platform, provides a better shopping experience for our customers, which is a very important goal for us. Now let's look at the current approach of implementing item to category mapping. So currently we are employing a rule-based item categorization process. So this diagram here depicts the end-to-end pipeline of item setup process. And for simplicity, what we have done is we have abstracted away the different components involved in the item setup. And instead we are showcasing just 3 boxes, as in on the left we have item setup upstream, in center we have rule-based item categorization, and on right we have item reingestion for downstream processing. So as part of the item setup upstream, we capture certain item metadata attributes to which are required for listing that item on the website. Now these attributes are passed on to the rule-based item categorization process. Now as part of this process, it applies certain rules and maps the item to their categories based on those rules. Now post this item to category mapping, those items are re-ingested for downstream processing. So this approach works pretty well for most of the use cases, but there are few challenges associated with this approach. Now let's look at what all different challenges we face. The first one is missing attributes. So since rule-based system have a fixed knowledge base, they also have a fixed intelligence. So if some important attributes are missing, it will result into a miscategorization of that item. The second challenge is the rule-based system does not consider a holistic view of an item. So since they lack the learning capabilities, they do not consider the existing item into the system, neither do they consider the relation of the current item with the existing systems. So it may happen that if during the item metadata capture part, if we have missed certain attributes or specified some attributes incorrectly, it may lead to a item miscategorization as well. Now the third important point is it's really difficult to scale such rule-based systems. So since this current approach is rule-based, the rules are the knowledge representation, and as the domain knowledge is encoded as rules, it becomes really difficult to those systems, and hence such systems suffer from a cold start problem. Like if there are new attributes added to the item metadata, the system may be stuck while processing it, or may not consider that attribute at all while the categorization process, because they do not have the knowledge to properly handle those newer attributes. Another problem which we face at scale is, as the knowledge base increases, adding new rules to the system becomes increasingly difficult, because those new rules can be in contradiction with the existing rules, and modifying those existing rules or adding new rules requires a significant engineering effort. Now, having seen the challenges, we proposed an unsupervised learning approach leveraging our retail graph and similarity search platforms. Now, let me first explain what all these two platforms I have just mentioned. So the first one is retail graph, which is an item-centric enterprise knowledge graph, where item being a core actor, it is related to different other entities into the retail domain. Now, some of the notable entities within our enterprise knowledge graph are like brands, product types, and categories. The second important component is our homegrown similarity search platform, which is called VAMOS and can be expanded as vectors NN managed search. So this is a similarity search platform for finding similar items within a given domain entity. Now, VAMOS manages the index entities and provides NN search, which is expanded as approximate nearest neighbor search against those index entities. In coming slides, we'll see how we are leveraging this synergy between retail graph and similarity search to improve the accuracy of item to category mapping process using certain graph ML algorithms. Now, this diagram depicts the proposed category mapping pipeline, where if you see on the left, we have item setup upstream, on the right we have item reingestion, and in the center we have VAMOS and retail graph. They work together to do the item to category mapping process. Now, as part of the item setup upstream, we capture the item metadata which is required for item setup, and then generate embeddings for those item attributes. Now, these item embeddings are used to do NN search against the indexed items within VAMOS. Now, item neighbors obtained from this steps are then converted to their graph representation and then fed to the retail graph system. Now, within retail graph, we run certain graph ML algorithms to recommend the category mapping for a particular item. Now, post this, those items are re-ingested for downstream processing. So as a whole, this system does the unsupervised way of recommending categories for a particular item. With this, I would conclude my part and would like to hand it over to Pradeep to cover the remaining slides. Thank you.
Thank you, Jitesh, for walking us all through the idea behind this item category mapping. Hey all, my name is Priyodip Mukherjee, and I would be walking you through the rest of this presentation, where I would demonstrate the algorithm and the high-level systems view for this use case. As on this slide, you can see this is a tri-step process to recommend categories for a new item in retail graph. In this slide, I will dig a bit deep into each of these individual steps involved. As we have already seen before, we feed graph-based item neighbors representation to the retail graph. On the left, we see a very simplified view of the graph schema with item neighbors relationship depicted using similar to edges. The nodes in blue are the new items, and the nodes in orange are existing items in the graph, which are already mapped to their respective categories, depicted using has category edge. The category nodes are shown in gray color. At any point in time, we will have this corpus of existing item nodes with their mapped categories. Also, the subgraph in the left shows that there could be an indirect association between the new item and the categories. With these potential category candidates for new items, in step 2, we create a bipartite graph by establishing a relation between new items and category nodes depicted with has category edge. I would like to give a one-liner about bipartite graph. It is such a graph whose vertices can be divided into two disjoint and independent sets, such that every edge in the graph connects a vertex from the left set to the right set. As you can see in the right, our bipartite graph would have one set in which we will have all the new item nodes ready to be mapped. And in the right side, we have list of all potential candidate categories for those items. In mathematical view, it is one-to-many mapping between new items to categories. And the final motive of this pipeline is to establish one-to-one mapping between these entity types. Once we have established this bipartite graph, in step 3, we run a personalized PageRank algorithm to recommend the category for any given new item. The personalized PageRank algorithm states that given a source node S and a target node T, the PPR value represents the probability that a random walk from S terminates at target node T, and thus it indicates the bidirectional importance between the source node S and target node T. Personalized PageRank is a representation of the importance of nodes within a given network. It is widely used in areas such as recommendation systems, fraud detections, etc. Thus, at the end of this final step, we would have a measure of this probability for all the edges between each of the new items to the set of categories each of them are linked with. And we contemplate to establish the one-to-one link for each items having the highest importance probability with the respective category. Now let's move on to the next slide where we would see the high-level systems view of our proposed approach. As you can see over here, this is the flattened view of our end-to-end pipeline. And this is just a one-dimensional representation of the entire system. In this slide, we talk more about the implementation part and different components that are involved to make this pipeline work. On the left, we see the item data store, which streams new items into our pipeline. The category mapper component is the interfacing component, which performs a set of tasks for each of the new items arriving in the queue. The first task is to generate a vector representation of the new items for its metadata using one of our in-house vectorizer service. This service takes into account the important attributes of an item and generates a feature vector, also known as embeddings, for it using large language models. In the second step, we use the vector representation of the new item to perform an approximate nearest neighbor search leveraging VAMOS. We have already described a bit about what VAMOS is in one of our previous slides. For this use case, the search is done against the indexed item collection within VAMOS, and it returns the set of most similar items for a given queried item, considering all its important feature vector. Once we have fetched the set of similar items for each input item, we offload these associations as a similar to edge for them to be ingested into our retail graph. At the end of this step, we should be having the new item in query mapped with a set of items by the edge similar to within the graph. Post these links are created, we formulate the bipartite graph for each of the new item nodes and the associated candidate categories. As a part of post-processing, which is our step 3, we run the personalized PageRank on this bipartite graph, generate the output links, and push the category recommendations to downstream for further processing. With this approach, we are attempting to reduce the item miscategorization gap. Since this approach not only considers the input item metadata, but it also kind of considers its relationship with existing items, which acts as an enhanced signal. It kind of thus overall improves the precision of category mapping, even in cases where there are missing attributes or incorrect attributes tagged to an item. This way, we remediate the non-holistic item metadata considerations with earlier approach. Similarly, as and when more attributes are added to the system, we can easily accommodate them by re-indexing the items within our Vamos platform. Also, as the graph grows dense and becomes richer, it will further elevate the accuracy of these recommendations. Over to the next slide. This slide showcases the result of our proposed approach. As you can see in the slide, our pilot graph has approximately 1.6 billion nodes and 7.6 billion edges. We can assume, looking at this volume, that we have hydrated our graph with considerable amount of data to run our pilot on. As for our Vamos platform, we have indexed a collection of about 500 million plus items. During the initial POC phase, we ran this pipeline with fewer attributes, and we managed to hit the accuracy number closer to the 60% mark. In the subsequent runs, we appended further attributes of item metadata, and post that, this pipeline has yielded close to 88% accuracy for us in its current state. Over to the next slide. Here in this slide, we talk about the future steps to be worked on to enhance this pipeline. The intent of these steps to be taken is to move the needle on accuracy. In order to increase the accuracy, we intend to leverage the graph embeddings algorithm like FastRP and NodePiece to generate a more holistic item graph embeddings for our similarity search step. These signals can then work in cohesion with the current search step and would definitely improve the precision metric. With this, we have reached towards the end of this presentation. I would like to conclude our talk here. I hope you guys had a great time listening to our talk. Thank you folks for joining this presentation. Have a great day. We are open for Q&A now.